All right, guys, we're starting now. The topic of today's lecture is pretty cool. It's agent-based modeling and simulation. So far, we have been focusing on various machine learning algorithms that are really about prediction. And in fact, all those algorithms were part of predictive analytics. And the idea for most of them was to review and determine patterns in data, learn the patterns, and then use those patterns to try to make predictions on the new data, right? Or maybe in the case of forecasting, sort of extend the series, the time series we have seen before. But in any case, the idea was to actually look at the statistical modeling. So we're looking for the patterns, we're modeling the statistics we observe in data, correlations in data, and then we're trying to predict sort of the next step, how things are going to evolve. The point is, we would never look into the actual mechanics or mechanisms of why this data has been generated or where it's coming from. Now, simulations are quite different. What you do is you start with some sort of fundamental knowledge. If we're talking about, say, physically based modeling, physical simulation, you start with physics, you can start with chemistry, you can start with engineering, or you can start with knowing how a particular process performs. So you start with some sort of domain expertise. And then based on that, you're building some simplified model, following that expertise, following the rules. And then you try to, simulate the results. You then verify the results you are obtaining against the data that you are observing. And then you can actually play all kind of what-if scenarios by changing parameters of your model. So here, the model is really sort of physically based, is based on first knowledge, right, of the processes. All right, so these are very, very different approaches. Now, within the simulation approach, one which is quite interesting is so-called agent-based modeling. And the idea is that we try to model large systems that consists of individual autonomous entities. And those entities, they are autonomous in the sense there's no centralized control, and they can interact with each other and because of that have certain behavior. Now, the sort of obvious application is to trying to understand and simulate social systems, right, where agents are people. But this is really not necessarily the case. You can think about different programs interacting with each other. Parts of the programs can be robots. It can be pretty much any system that can be decomposed into independent subsystems and that interacting with each other. In fact, one of the most interesting things happens when you get a lot of those autonomous agents. And sometimes within the business environment, they're very well structured and connected. Or when we're simulating, for example, social environment or social mechanics, you will get agents interacting with each other in various fashion. And in fact, you can observe very interesting behavior. We're going to talk about this, some sort of emergent behavior of those large systems. Another example of those is like microservices or microservices architecture, something that comes directly from computer science, computer engineering. But if you think about this, these are also agents, right? You have different services. Each of them is independently deployed and support. They're coupled but loosely coupled, which means they just interact through different APIs, and each performs very particular function. Agent-based modeling is used a lot in business. Some of those most popular applications, again, are those places where it is hard to build good, solid predictive models, and the challenge usually is because of the interacting parts of the system, because there's usually large systems interacting with a different behavior and different performance. So, for example, that has been used in marketing when you try to simulate competitor behavior, or when you try to simulate consumer behavior, depending on the prices, what's going to be happening, right? And you can actually add some randomization to this to calculate and see what's going to simulate the result, right? Simulate consumers buying products or product switching. Definitely simulation within a business process and optimization, where you have a particular business process, your business going through, you can simulate how long it takes to go through each step of the process and try to find bottlenecks through those simulations, or play various scenarios. If you change certain patterns or change the connections within the processes, if it's going to run faster, slower. Extremely popular usage is within the transportation, where you do have, again, like sort of, if you think about very simple traffic control, where you have cars arriving at the intersection at different time moments, calculating how they're going to cross intersection is like literally almost impossible from the mathematical modeling, but you can do it with simulation by providing simple rules for every agent, or even traffic jams. But then there is like very, very popular application is in fact is logistics, is within operations, when you actually design supply chains and trying to simulate how long it would take for the supply chain and how much it's going to cost and how long it would take to deliver goods from different factories through warehouses to final delivery, right, to the final user. And of course, all kind of production planning on the plant, it also can be done through simulation. We in fact used a little bit of simulation when we looked into actually we didn't look at it. I forgot. So we could have used it for example, epidemic simulations to actually calculate how disease spreads in a particular environment. So there are a lot of applications, again, from pure scientific to very, very much business type of applications. Now, there is some software out there that allows you to do this. There was any logic software. There are like Python libraries. Quite often software comes with this 3D graphics. Obviously you don't need 3D graphics for the simulation. Again, agents are not really those 3D metaverse characters. They're mathematical entities with certain properties. But you can visualize them definitely using 3D graphics if that makes customers happy. So why and when we use this agent-based modeling? Well, the real-world systems are becoming very complex and interdependent. So there is a lot of dependencies within the systems, and those dependencies sometimes unpredictable, and parts of the system behave unpredictably. The question is how this complex system behave when you connect those pieces together, but each component can follow some simple standard fixed rules, but even in that case, the system as a whole may behave very, very differently. Quite often we experience decentralized decision making, and that is sort of what agents are about, right? Where every agent makes its own decision, and we want to see and model dynamical situation where how things evolve and change with time. Finally, in business, you often want what-if scenarios, and so those scenarios you kind of plan your strategy and your tactics by playing all kind of what-if scenarios, trying to simulate what's going to be happening. So what's agent and what's agent-based simulation? Well, first of all, we need to define an agent, and we define an agent as a separate entity that exists within a larger environment and can interact with that environment, can possess certain perception, so can sense signals, can receive signals from the environment, and can perform actions. Now, again, actions here, we're not talking about robotics. Not necessarily you need the agent to be able to sort of move arm or hand or move stuff, but it could control, robot if needed. So again, we need to define an agent, we need to define relationship, we need to define an environment in which the robot, or agent lives. So what's inside agent? Well, every agent can have built-in rules. And agent is autonomous and is decision-making. Decision-making means depending on the situation in the environment and the perception, the signal that comes from an environment, agent makes a decision what to do next or how to respond to that situation. Now, here we're going to be talking right now about very, very simplistic agents with built-in fixed rules, literally like what-if rules. But you know, at the seminar and at the very end, we'll also mention sort of the latest and greatest ideas of how we can use LLMs to actually build AI-controlled agents. So the key here is, again, every agent can make decision, and decisions are made by each agent independently, but you know, in response to the environment, and the environment can be changing. Now, agents can be homogeneous, so you can have the group of similar agents, if you want to model social dynamics, or it can be very heterogeneous and diverse. Now, agent would typically have internal memory that memorizes the states, or maybe some sort of stack that gives you preferences of actions. And it can have an internal model of the world, meaning agent can actually sort of predict how the world will change depending on the action of the agent. But that's, again, that would be more of AI agents. So if I want to simulate agents, what do I do? Well, we need to define the agents. We need to define the relationships between agents, and we need to define the environment. We don't need a central controller. And then every agent will move according, or will behave according to the rules that we put into the agents. We can define interactions in between agents. The agents can be interacting like completely pairwise, or with the selected other agents. It's up to us. And we can talk about various topologies connecting agents. They can live on the network or interact through the network, like network of friends, sort of thinking about Facebook, or they can be some other type of agents. And you can think about optimization for the entire system for the bunch of agents. Now, what's important also that all those agents, they're dynamic, which means they behave, operate with time, and there is sort of single synchronized clock that exists for all the agents. Well, the same as in our life, right? The time is going by, doesn't matter what each of us does. Now we're going to look at a very simple example of agent-based modeling, but it is like absolutely classical example by Thomas Schilling, a Nobel Prize winner, which is described in his book on dynamic model of segregation. It's became like a classic within the modeling, and it shows how small changes and very, very simple rules for agents can lead to a very, very diverse and surprising global behavior of the system. And so within the spatial model of segregation, the paper talks about the fact that when people populate cities, they in fact segregate, which is people, in his discussion, in his paper, he talked about the race and the fact that when you look at the cities, people of similar race tend to live next to each other. And then when you look at the entire city, you will see it being completely segregated, which means there are regions populated, which is regions homogeneous, populated with the same race, and then there are quite sharp boundaries with the regions populated with other race. And the question he was asking was that, like, is this something that people are so racist, or sort of what's, why is that happening? And to answer that question, there is no simple mathematical model to answer that question, or to see this, to predict this performance, to predict the results. So he resorted to simulation, and so he proposed a model. So and in fact, he did the simulation, and it is 1971, right? So 50 years ago. So he literally did a simulation with a pen and paper by drawing how the system will evolve in time. And so what he was shown that the particular small preferences for each person can lead to a very synchronous collective actions. Sort of micro motives will change macroscopic behavior. So small changes in the behavior of each agent can actually affect significantly the behavior of the entire system. So what's his model? Well, his model is very simple. Assuming that we live on a grid, right? And it's housing market, and sometimes this is called the housing market simulation. Where houses are located on the grid, and population consists of two types of agent, right? Here, red and black. And agents can reside anywhere in the cell. So for every agent, there is 8 neighbors. Some of them populated with agents, some not. And again, you can think about this simulation as renters market or housing market, buying market, doesn't matter. But every agent wants to have no more than some fraction of neighbors that are unlike him. You can think about race, or you can think about income. So, people can tolerate, 20% of people of lower income, or 50%. If they're very tolerant, they'll tolerate like 99%, right? But so the game is the following: on every round, every unsatisfied agent can move to an empty cell that satisfies him, and this continues until everybody is satisfied or there's no place to move. So again, extremely simple. Every agent is identical, except there are 2 classes of agents, but each and every agent has built-in identical mechanism, identical behavior pattern. So if all the neighbors, if the neighbors contains more than some threshold number of people unlike him, the agent will relocate. Otherwise, will stay. And there we go. That's your simulation. So what has shown that sometimes, and this is the start of the simulation, what has shown as the time progresses, that though at first you can start with a very, very mixed society, but even if the tolerance level is 50%, so everybody is happy having 50% of neighbors of different color or different type. As the time progresses, the city becomes completely segregated. So you literally go from this mixed environment to segregated environment, where you get, when all the reds live where they are and blues where they live. You can see this on the picture. Now, again, the interesting part is extremely simple rule, but leads to this type of consequences. And he has also shown that, depending on depending on this threshold, you can still get this type of behavior. Even if people are quite tolerant as a group, as a society, it will lead to segregation. Even if people, and here as you can see the different simulations, even if people are very tolerant and are capable of accepting quite a significant fraction of their neighbors of being a different type. And that behavior doesn't change even if you have a lot of spare locations to move, as shown here with empty dots. But you can of course change this behavior by locking people down or by removing empty spaces to move. But when the system evolves the way it evolves, based again on this very, very, very simple basic rules, it gets to the setup where from completely random, you get to very segregated. Now, the point of this exercise is really to show you that the very, very simple behavior of a large system can lead to some sort of quite unusual global behavior. Sort of its micromotives leads to macro behavior. This phenomenon is also called emergence. So where we started with this disorder, and then we got quite ordered system where you have reds on one side and blues on another one. And that happened quite abruptly. So that's just a simple example for the modeling system. And in fact, you can find probably online a lot of software where you can play with this type of simulation. But of course, for business, we will not simulate most likely the housing market this way, right? Unless you're like an economist or really working for one of those developers. But most likely you'll be focusing on simulating, for example, supply chains. And within the supply chains, there are different parts of the supply chain that you typically take into account, right? There are customers that sort of we're going along let's go along the value chain. We start with the factories where things produced, through distributors, to the wholesalers, to the retailers, to customers. And there are flow of orders. We talked about it when we talked about retail, that goes through customers to retailers to wholesalers, to distributors, to factories to produce stuff. And then, shipments going in the opposite direction. And you need to calculate for each level, how much to ship. Moreover, how much to ship to which distributor, to which wholesaler. And even better, since on each of them, it takes some time to ship, so you need to take that into account. And then there is, time to process the shipments. So all this is very, very challenging to calculate. Now, in fact, supply chain modeling, you can do integer programming and overall optimization. But quite often, even after you've done that, you try to run a simulation that would actually simulate this process. Eventually, the simulation controls how much stuff has to be produced by factories, and how much has to be distributed and through which channels. So here's yet another picture for the supply chain modeling, where we're talking about orders going from downstream to upstream, and upstream means to manufacturing, and downstream means to retailer. And so you can actually think about each of these steps of this process being an agent. And agent with a bunch of parameters, like factory agent, there is middleman agent, there is supply chain agent, right? There are customer agent, and every agent has internally memory, sort of the state, right? That writes in orders, et cetera, et cetera. It can actually have some machine learning systems that do forecasts for him, and then those agents start interacting. Now there is an external clock that makes that sort of ticks and makes the simulation synchronous. But other than that, every agent has his own rules, right? And has his own goals, which is very important. So here, agents are different, right? There are receiving agents, there are shipping agents, there is purchasing agents. In each of the agent optimizes his own internal function. Based on the goal setting, it actually interacts with other parts of the system. So, but here again, most of the rules are hard-coded and built in. The only thing we use here in terms of machine learning is, we can do forecasting, right, on the different levels. Here's another example. We can actually model behavior of different consumers for, in this example, for large B2C commerce, where you look at different prices, at product information and all kind of information, trying to simulate and predict. Here it shows like market share for a product, but you really try to predict the volume, the purchase volume. And there are consumer agent, which is consumer with his own properties like sensitivity to price or sensitivity to the quality of the product, and then some demographic characters. Then there is manufacturer. Then there is a seller agent, which determines the price and the site. And then there is a marketing agent that determines the marketing. And so consumer agent can be affected by the marketing. But what's more interesting is consumer can be affected a lot by other consumers, seeing that other people buying it. And so behavior of every agent will depend on the behavior of other agents. So in this way, you get multiple agents, which are identical like customer agents, interacting with different type of agents, which are seller agent or the store agent. Now, each customer agent internally identical, but might have different preferences. But each customer agent can interact with other customer agent and can be influenced by other customer agent. And so his purchasing behavior will depend on the purchasing behavior of others. Now, this type of system is a very complex system. It's very hard to, in fact, model it from the first principles. It's actually not even clear how to do this. But it is very clear that you can specify very particular precise rules for every agent, how it behaves, then make the environment, figure out the connections, which agent interacts with which, and put in rules for the agents how to operate depending on the environment. Say price drops below X, you buy, right? Your three friends purchase, you also purchase this item, etc., etc. And based on that, there are various simulations that can be done depending on the product and the cost of the price of the product and other properties. So this is all sort of simulation, agent-based modeling in action. Now, in spite of the fact that it can be quite useful, the topic of agent-based modeling, there is some sort of, it was not as popular as traditional data science. And there was some number of software, there was some number of people who knows how to do it. But it is quite helpful, especially for the large companies. Now, I think we're getting into the time when this is becoming really, really interesting, because we're getting to the point where we can literally build autonomous agents. And autonomous agents means that instead of us providing a very strict decision-making rules to the agent, right? Literally if-then rules, we'll let LLMs, large language models, be those agent brains. And so with this scenario, we have a system that is capable of executing very high-level tasks. GPT or other LLM can be used to create tasks, to take the large task and split it into small tasks. Can be used to do task prioritization. You probably need to add some memory so that agent will remember the state. And then you can execute. And can execute through, for example, connecting to external tools. So that is a very popular topic right now. There is like software like AutoGPT, Baby AGI, and others. All this is put together through like LangChains. It's open source, and there's going to be a very, very interesting development in this field. So I strongly recommend you to learn that stuff, at least if not coding, but at least the concepts. And in the seminar, you either did or you will work on this type of autonomous AI-based agents. And as always with the literature, well, there's still, of course, no literature on AI agents. This is so new. But here is a book on agent-based modeling and interaction, which is, in modeling through using the well-known NetLogo library. There is another one, which is AnyLogic. These are two systems that are often used in practice in business. Again, if you're a Python coder, there are libraries that allows you to do it in Python. And with that, we're done for today. Any questions? All right, if there's no questions, we're done. Thank you.